Um, so I want to talk about the advantages of using a curved image plate for rapid laboratory-based X-ray total scattering measurements. And this really, it's been a kind of a journey over the last few years, as you'll see as we go through the presentation. So this is work that we've been doing at University of Southampton. And this little picture here, this shows the brick building is the research part of chemistry. So that's where the X-ray instruments are on the ground floor. And the grey building is a newly refurbished undergraduate labs, which were finished pretty much just in time for the first lockdown. So that was a bit of a shame, but we're hoping the students will be back in there soon. So one more pretty picture before we start. This is our lovely Highfield campus. This is obviously in the summer and also pre-COVID. Looking at the shadows and also the lack of students around, I guess this was quite early in the morning. So on to my talk. So this is going to be split into two sections. The first part, I'm going to be talking about the instrumentation we've been using. This is an instrument called the Spider, which I'll explain in the coming slides. And we've been using this to collect total scattering data. And initially we were using it, or we were kind of benchmarking it using PDF analysis. And then in the second part, I shall look at some initial results where we've gone on to look at something actually quite different, especially from the rest of the presentations today, where we're actually going to be looking at some liquid samples. So I said this was kind of a journey, and as Takayuki said in my introduction, I've been sort of doing X-ray scattering for quite a number of years, and reasonably recently I kind of decided to maybe change tack a little bit and move in a slightly different direction. So it was kind of a personal motivation to kind of get into total scattering. And also it came as a kind of a need within the department to kind of expand what we can look at with X-rays. They kept stumping me with their questions about how do we analyze their samples. And also we've actually been kind of repurposing an old instrument. So something that wasn't being used an awful lot has now kind of found a new lease of life. So those sort of three things came together to send us along this journey. So now I'm going to talk about the instrumentation. And this is work which has recently been submitted for publication. And this is the instrument we've been using. So this is a Rigaku instrument, probably less common than some of the other ones you've seen. And in the version of the instrument we've got, this is called the Spider, which I believe stands for Single Photon Imaging Detector, but maybe someone from Rigaku can either confirm or deny that. And it is an instrument that is still marketed, I believe, as the Rapid 2. So I should point out that this was actually originally sold as a single crystal diffractometer, and we have used it as such over the years with copper and molybdenum tubes. But when we started the total scattering work, we obviously put a silver tube in because this gives us the best Q range. So this is all important, as you'll hear in some of the other PDF talks, being able to collect data to a high Q. And this is what the numbers in white are for the radiations here. So silver has the largest Q max of available tubes. So we also have a monochromator giving us alpha 1, alpha 2 radiation. So it cuts out the bremsstrahlung and the K beta. The goniometer here is a 3-axis goniometer, although to be honest, we probably only use the phi for our PDF work. So we only rotate the sample around the phi axis. The beam is a collimated beam, so it's a circular cross-section beam. And the detector is situated at 127 millimeters behind the sample. And that's something we can't change. So our detector is not movable. And it's the detector that's kind of the unique feature, I guess, of this instrument. So it's an image plate, so quite old-fashioned technology, especially with all the developments that we've seen recently. But it's actually really well suited for this kind of experiment. And in this case, it's actually curved, so it's curved cylindrically around our sample, which gives us a range in 2 theta of -60 to 144. So our positive direction is kind of going to be to the left in this diagram. And it has a large dynamic range, which is useful if you're looking at very crystalline materials where you also want to pick up the diffuse scattering. And the sort of exposure times we're doing here are sort of an hour, 2 hours, maybe 3 hours. So the other nice thing about an image plate is the very low inherent noise you get with the detector. So these images are obviously zoomed in parts of the detector, taken behind the beam stop. So this is an area where we shouldn't really see any scattering from the sample. And if we look after 10 minutes, we get these sort of counts. And if we come and look 180 minutes later, we see very, very little difference. So this is great because it means we can just leave this collecting for literally hours without significantly increasing our background noise level. So on this slide, we have these beautiful images. So these were taken with lanthanum hexaboride, obviously a classic material you've already seen data from today. So this is the full image, and things are going to sort of appear back to front in the sense that I'm going to be looking at low 2 theta on the right and higher 2 theta going towards the left. So what I've detailed here, so the Q max, so the maximum Q value you can obtain with silver radiation is 22.4. So that would assume that your 2 theta scattering angle is 180 degrees. The way our detector is positioned, the very edge, this left-hand edge here, sits at a value of 21.3. And in fact, we use a little bit less than that because of the way we integrate our image. Now, you won't be able to see on your screens, but just to kind of prove that we are seeing scattering this far out, this is going from sort of 130 up to 140 plus in 2 theta. So the blue is our measured data. So we're getting nice peaks all the way out there. And in terms of D-spacing, that corresponds to about 0.3 angstroms. So to integrate our image, to go from the 2D to the 1D profile, we use the Rigaku 2DP software. And as you can see, we do currently end up throwing away quite a lot of our image. So this is the area we include in our integration. So this has a constant chi value. If we try and integrate the whole image, which I'm sure is possible, but it becomes a bit more complicated because you've got to scale it because you're using different parts of reciprocal space as you go across the theta range. So this at least is constant and means that we get the correct intensities out. So when we do this integration, we correct Lorentz effects and also polarization. We have a monochromator in the system, so we do see some polarization. So the data reduction, which is the all-important step in PDF analysis, we currently do using GudRunX, which is freely available software from ISIS, so the neutron source in the UK. So you can follow this website and find some useful information about that. And there's kind of 2 sides to this. The first is obviously the measurements we take. So we measure our sample in a capillary. We also need to measure the empty capillary, or the container as we call it. And in addition, we also need to measure the diffractometer with no sample on it. So we've got 3 measurements here. So if your measurements are taking a long time, so some instruments might take 12 hours to collect data, you've you've kind of got to multiply that by 3 because you've got to do 3 measurements, or unless you scale some of these background scans. We also need to know about our instrument. So we need to be able to tell the software the geometry of our goniometer, the beam profile, and the sample geometry. So the inside and outside dimensions of our capillary, etc. And we feed these into our GudRunX processing software, and it will make corrections basically for everything that's not our sample or not the structure of our sample. So we correct for absorption, multiple scattering events, non-sample scattering, Compton scattering, and also we scale to the total sample scattering cross-section. So this is, I'd say it's not exactly straightforward, and it's an iterative process, some of these steps. But at the end of the processing, you can output your data in various formats. The 2 I'm mentioning here, the first one is the differential scattering cross-section. And we'll see this is what we use for looking at our liquid samples using this software approach, EPSR 26, which I will talk about a little bit later. And obviously, if you're looking at pair distribution function, you can output what is effectively the Fourier transform of this first file. And you can output this as the G of R or the D of R. So these are different pair distribution functions. And you've got to be a little bit careful to make sure you're using the one that your software is expecting. And you'll even see that sometimes these 2 are actually interchangeable in some software and not in others in terms of what they're actually defining. So you do have to be a little bit careful. So basically what I'm going to do is go through a number of tests that we did, basically to convince ourselves that our instrument was collecting data of good quality. So the first thing we did is look at LAB6 because this is a strong scatterer, so we can use it to see how well we are integrating our data. And I should say that for all the work in this first part of the talk, we used Topaz Academic for our refinements. So actually the first thing we did was not a PDF refinement, we did a Rietveld refinement. This was just to convince ourselves that the 2D to 1D integration was giving us usable data. So we got a great Rietveld refinement, so we were happy that the integration stage was working well. And then we did our PDF refinement. So here we have in light blue our experimental PDF, so calculated from our measured data. And then in dark blue, we have the model fit. So we got a good fit, and we seem to kind of lose information somewhere around 80 angstroms. It's always a bit subjective exactly where you start to fit noise as opposed to fitting real information. Now, one thing that came out of this was actually, this is not a great standard to use for PDF because it's dominated by the coherent scattering, which means your data correction isn't having to work too hard. Which basically means even if your data correction is not doing too good, you'll still probably get quite a nice refinement. However, it did give us an instrument kind of signature that we could start to build on. So then decided to look at silicon, another classic X-ray standard, which I think is more representative of the sort of scattering you'll get from a lot of samples, and also means we can probably compare this to other labs because everyone has silicon. Again, we did the Rietveld refinement to obtain the instrument parameters that are required for most PDF type refinements. So these are effectively beam shape parameters. So DQ is our beam profile width. We then have the Lorentzian contribution to the pseudo-Voigt peak shape and the mixing parameter alpha. So again, we get a nice fit with a fit going up to a similar kind of resolution of 80 angstroms in R. So we then had a look at annotate, so some nanoparticles, because these are quite nice to study with PDF, because you can use your fall off in the PDF signal as a way of measuring the nanoparticle size. And in Topaz, you can do this by refining the spherical damp value, which is effectively kind of working out where you start to lose pairwise correlations in your data. So this is not plotted as high as some of the other plots, which went up to 100. So we actually lose this information at about 46 angstroms. And if you compare that to just looking at the peak width, so looking at the corrected full width half maxima, that gives us a value of about 56 angstroms. And these are actually sold as 5 nanometers or 50 angstrom nanoparticles. So these are all kind of telling the same story. So we knew we were getting good data. We then wanted to kind of see how long we really should be collecting for. So we're now looking at some amorphous materials because these scatter less strongly, and we thought were a better way of judging exposure time. And I've now plotted the total structure factor or structure function, depending on the terminology you want to use, as this kind of clearly shows the noise that we see. So these are kind of typical total scattering plots for amorphous materials. And obviously, as we collect for longer, we get an improvement in noise. Although it maybe looks like we're kind of reaching a point of diminishing returns around sort of 240 minutes. I really should increase this graph and plot some data that's collected for much longer just to kind of complete that story. But if we look at the corresponding Fourier transform here, back to our PDF, obviously this is an amorphous material, so we tend to see fewer peaks. These are kind of the peaks from the tetrahedra type pair correlations, so the direct bond lengths and nearest neighbors, etc. And what we see as we count for longer is that these high frequency ripples at sort of higher R flatten out, as does the detail in the low R. So this theoretically should be flat, kind of below about 1 angstrom, because we don't have any pair correlations that small. So this kind of is what you see as you reduce the noise in your signal. So this is where we are counting statistics wise in this kind of area now. So to conclude that kind of first part, we've convinced ourselves that we're getting excellent data from our instrument, although we have seen that it's kind of limited by the lack of beam focusing. So that's the reason we lose information at about 80 angstroms, is due to the peak width in reciprocal space of our reflections. So we can envisage a much better instrument, or an even better instrument, where we could potentially move the detector so that we're not throwing away so much data. Obviously a more intense source, so a rotating anode, and some sort of focusing beam optics rather than a monochromator. So that would kind of be on my Christmas list. We've also concluded actually it's really great to have an instrument like this in the lab, just because you can go and collect data reasonably quickly and try out all sorts of ideas, because obviously, as we all know, most of those don't work, but it gives you that opportunity to find the ones that do. And more on a personal kind of comment, you'll read in some places that total scattering is kind of much more routine, and you do see it a lot more in the literature, I would say, but it still requires quite a dedicated effort to work through collecting and correcting data. So in this second part, I want to briefly look at some results that we've collected within the last year, probably. And these are going to be looking at, say, aqueous systems, which came from talks with colleagues who are very interested in crystallization. So the big picture here, or big aim, is to kind of see whether we can get information on the structures forming in solution just before the crystallization begins. And to do that, we've used an approach called Empirical Potential Structure Refinement, or EPSR. And apologies if I automatically stick a C on the end of that, because as my UK colleagues will know, that's our national funding body. So that's what my brain tends to say if I'm not thinking. And what this approach does, this basically attempts to find distributions of atoms which are consistent with the experimental data and constraints. So we're obviously working with a very underdetermined problem here. So we kind of have to tell it as much information as we can. So at the heart of this approach is a Monte Carlo type simulation. And we feed into that information about our system. So we have reference potentials to model the interactions of particles. So these are sort of a very basic Leonard-Jones type potential, plus a Coulombic term to deal with charges. We also have information about intramolecular structure. So I'm going to be looking at some sulfate structure, so we know the geometry of a sulfate. And we know the density of our solution and the composition. So there's quite a lot of information we can feed in. And we can run a simulation without any data at all, which will, we can minimize the energy of that. And from that, we can calculate a radial distribution function and onto the structure factors. And then this is where we feed in our experimental data. So we can calculate the structure factors from our total scattering, and we can then use the difference between these and our model, and we encode these in the so-called empirical potential from the title of the approach. And this we feed into basically perturb our simulation and drive it to a place where it now matches our sort of reference potentials, but also more importantly, our experimental data. And we can use this approach for crystalline or amorphous materials. So a really nice way of doing this is if you've got crystalline material where you've got Bragg data as well as total scattering data, you can use your Bragg data as a restraint on your system. So the first thing we had to look at was water, and basically this is because I'm super paranoid about trying to run before I can walk. So we wanted to look at a system which is well known, which water is, although people do still argue about exactly what's going on with the structure. But hopefully this will introduce you into the approach that we've been using here. So we have our experimental data, and we're now looking at the F of Q, so we're in reciprocal space. So this is in light blue. So this is measured on our lab instrument. So it's always quite surprising to me that you can put water on a diffractometer and measure a signal. And then we have a model, and our model here consists of 10,000 water molecules, and we calculate the fit, which we have in dark blue here. Now, that's all very well, fitting our model, but it's very difficult to actually describe what we're seeing in this large box of molecules. So one of the ways we can do this is to look at these spatial density plots. And what we're seeing here is we're looking at the 10% most likely positions to find another oxygen atom around a central water molecule. So this, we got the expected result of a sort of pseudo-tetrahedral environment. And if you expand your percentage you're plotting at you get the second solvation shell starts to appear, and this has a sort of anti-symmetric relationship to the first shell. And so I've referenced down here a paper by Alan Soper, who's done a lot of work in this area, and they're nice readable papers, I find. So it's a fascinating story all about water. So briefly now, just a couple of slides on the work we're carrying out currently. So this is looking at aqueous magnesium sulfate. And the model we've looked at here is around about 2 molar, which is more or less the saturated solution level, because we want to look at it just before it crystallizes, and also the more saturated it is, the stronger the signal will be. So in fact, this was a combined study. So we have the X-ray data at the bottom here from our SPIDER instrument, and we also measured some neutron scattering with some isotopically substituted samples. So a deuterated sample and a 50-50 deuterated, non-deuterated, and then a pure water sample. So this just gives us much more information into our system. The neutron scattering is probably more sensitive to the water structure, and the X-ray more sensitive to the metal salt. And I should say that you can, if you join the poster session after this talk, Dan has got a poster there. Dan's studying for a PhD with me. So there's a bit more information than I've got time to show here. So this model then represents our fitted data. I haven't included the water in this picture, otherwise you wouldn't really be able to see anything. And it's worth noting that the refinement when you don't include your experimental data, so just based on the reference potentials, looks different. That effectively gives you the most random kind of solution. When we introduce our data, that's when we start to see clustering. So the ease, or one way to look at obtaining or kind of describing what's going on in our model, is to look at such things as coordination number. So this plots the average coordination number of magnesium in dark blue with respect to water, and in light blue with respect to the sulfate. So we can see that the most likely coordination number for magnesium is 5, and that's to 5 waters. And we can look at this kind of in tandem with the sulfate, because the other place in that octahedral environment is taken up by 1 sulfate oxygen. So over here, this is the most commonly observed environment around magnesium. So they're effectively charge pairing in a solution. The next most likely is 6-coordinate magnesium to water, so a purely hydrated form. Again, probably not at all surprising. And then the remaining, or of the majority of the other situations, where we have 4 waters and 2 sulfates. And we haven't investigated further here. These could either be in the trans configuration, which gut instinct would tell you is the most likely, but we do also see some in the cis. So these graphed are the statistics, and these are pulled out of our actual model. So we sort of literally dived into our aqueous solution and pulled out examples that tell the story of our statistics. And we can also look at our bond angles around the magnesium, which we've plotted here. And so the light blue is those water where we're sort of fully hydrated, which gives the most, or the tightest kind of distribution at 90 and 180, as we'd expect. The reason that the peak is highest at 180 is because of the way these angles are calculated. To get the proper distribution, where you'd get more at 90 degrees, you need to divide this by sine theta. But that causes problems at 180 degrees, because you're effectively dividing by 0. So that's why it's plotted in this form. But it's obviously a bad color choice here, but the black peak is looking at the situation where we're looking at the sulfate, magnesium sulfate angles. and these are pushed to a higher angle, and they've also got a broader distribution. And you can understand that if we're kind of forcing adjacent groups apart. So that's nice because it means that we can kind of form a coherent story about what we're seeing in our structure. And obviously these do not add up to 100%, so we've got other things going on in a solution. We also see examples of chains starting to form, and also higher coordination than 6, as well as lower. So really that's where we are currently. So this is very ongoing work, which we've not published yet. But we've kind of seen that the spider is ideally suited to looking at these amorphous samples, which are dominated by incoherent scattering. I found that this EPSR approach, which was new to me a year or so ago, is a really nice way to look at systems that we'd struggle to look at in other ways. And I guess a couple of take-home messages that, like with any restrained refinement, we've got to be very careful about what restraints we use, because in an underdetermined problem, it's less obvious if you use a restraint which is inappropriate. And it's also very important to understand the information that is contained in your experimental data so that you don't ask too much of your data. So that's why it was nice to have the neutron data as well in the case I've shown here. So onto my acknowledgements. Most of this work, or pretty much all of this work here, was done by Dan Irving, who's, as I said, studying for a PhD with me. So he would like to thank the EPSRC, which I do mean a C on it this time, for our funding. I'd like to thank David Keane from ISIS, who's provided a lot of time kind of discussing this total scattering in terms of data processing, etc. Tom Hedden at ISIS, the Sandals beamline, he oversaw the work, the neutron scattering. And I'd like to thank you all for listening, and got time, I think, for a few questions that I shall try and answer.